Hello everyone, welcome to the second video of the part of this course on machine learning. So on this video we will see some very short recall of statistics, and then we will see a bit of statistical learning theory, which is the more theoretical part of machine learning. Okay, so statistics is splitted generally in two parts. You have descriptive statistics and inferential statistics. So descriptive statistics, first of all, is a way to summarize data. You have a variable or several variables, and you want to have a single value that allow you to describe and to analyze those variables or this variable, depending if you have one or more. So it's a very useful tool because if you have, let's say, 1,000 example, you cannot look directly into the data and just analyze value per value the data. It will be very tedious and impossible if you have a lot of data. If you have only 20 data, you can just open it on a spreadsheet and look at them and analyze them. It may be sufficient. But if you have a lot more, it's good to have one value or very few values that describe well your data. Okay, so these are called statistics. A statistic is a measure. So the most famous one is in the first row of the slide is the sample mean, also called average. So in this case, the mean is noted x bar and is equal to the sum of your value divided by the number of value. So you applied it on only one variable, one feature, if we use the vocabulary of machine learning, and it output you one value. So the average is a measure of the center of your data. It allows you to see where is the center of your data. So, but it's the one problem with the mean is that it's affected by outlier. So if let's have an example. So for example, let's say that we have one feature that for 99 example have the same value or equals to 1. And you have one example that is equal, the value is equal to 1,000. So in this case, you see that all your values are equal to 1, except one that is equal to 1,000. In this case, it kind of makes sense that the center, if you have to give one value to represent the center of your data, it will be 1. But if you take the average, it would be equal to 10.99 because you have this one example that push up the value, the mean toward the high values because it's very different from the other. So this is why we said that the average is affected by outliers. So you have to take it in mind that when you look at the mean. So for example, if I may take an example, generally statisticians don't look so much at the average of wages, of salary. Generally, we prefer another statistic, which is a median, which is on the second row of the slide. And the median is basically the middle value. If you have a bunch of data, a bunch of example, you order the values of the feature you want to analyze, and then you take the middle one, the middle value. So if the number of example, the number of values that you have is odd, you take the middle one, and if it's even, you average the two in the middle. So think of a median as that you have 50% of the data that are below the median and 50% of the data that is above the median. So you like the sample mean, you applied it to one feature. And it's very useful because it's also a measure of the center as the mean, but it's not affected by outlier. So think of, for example, when we have 99.1 and one value that is equal to 1000. So in that case, the median will be 1 because you have 50% of the data that are less or equal to 1 and 50% that is more or equal to 1. And in that case, the 1 point that is equal to 1000 doesn't affect the median, because if you only change its value and you set it to 10,000 or more, it doesn't change the median. But it will affect, it will change the mean. So that's why people generally prefer to report the median of wages to have an ID to represent what is a typical salary inside a company, for example. So it's much more a much better representation than the average, because in terms of salary, you have a lot of discrepancy. You have a lot of different value, and you can have a big wage of the CEO, for example, that will raise a lot the mean of wages, but it doesn't mean that the typical employee of the company will have a bigger wage than another company that have that pay less his CEO. Okay, so that's why generally people prefer to report medians when we look at wages. One very important another value that is really useful is standard deviation. Statisticians really love standard deviation when we report the mean, and it generally comes with the two comes together. So if you report the mean, generally people love to statisticians at least love to have standard deviation. Why? Because standard deviation is a measure of variation. It kind of represents an average distance from the mean. So as you can see, it's equal to the square root of the sum of the distance from the mean that is put to the square and divided by n minus 1. Okay, so if you take only the center part that is under the square root, it's called the variance. So the standard deviation is the square root of the variance. Okay, so standard deviation is really useful because it allows you to have a complementary view on average, because the average will give you an idea of the center, but it doesn't give you much information on how widespread and how much value is taken by a variable. So you can see that the standard deviation has allow you to see if a feature is very compact, is very center around the center, it's very let's say all the value gathered really close to the center, or if it's really spread up and it can take a very large variety of values, and it takes a lot of different values that are very spreaded. And there is also the last one, the last famous statistic is the correlation coefficient. It's also called the Pearson correlation, and it represents, in this case, it's applied to two variables, whereas the three first that we saw apply to one variable. So in this case, you want to measure the linear relation between two variables. So it's useful because if sometimes you want to see if a variable is correlated to another one, if it's positively correlated or negatively correlated, which means that there is, if it's positively correlated, it means that in average, if you take the one of the features, the other will have will be related to it and will have a high value too. If it's negatively correlated, it means that if you take a high value of one, the other will have generally a small, in average, a small value. So it's useful to summarize in one way the relation between two variables. And this correlation coefficient is can take value from -1 to +1. If it's equal to +1, it means that it's positively correlated. It means that there is a dependence in the same way. If it means that high value of one corresponds to high value of the other, and low value of one corresponds to low value of the other. If it's negatively correlated, then it's closer to -1. It means that if one of the features is high, then the other is low, and vice versa. If it's equal to 0, it means that there is no linear relation between the two. So this can mean that there is some kind of independence between two variables, but it doesn't. It's not necessarily the case. It can. So if I can show you a counterexample, imagine that you plot in the y-axis the first variable and in the x-axis the other variable. Sorry, the reverse. In the x-axis, you plot the first variable, and in the y-axis, you plot the second variable. If you have kind of a U shape, then you see that there is a relation between the two, because you can clearly see a U shape. And but if you compute the correlation coefficient associated to those data, you will see that it's equal to 0. So keep in mind when you analyze the correlation coefficient that having it equal to 0 doesn't mean that you have necessarily independency between those two variables. Okay, so to summarize, descriptive statistics are really useful if you have one or several features and you want to summarize them in a single value. The other part of statistics, as I mentioned, is inferential statistics. In inferential statistics, the main difference from descriptive statistics is that in that case, you suppose that you have a population and you sample from it, and you observe only the values associated to the sample that you have. So let's take the example of the height of people, So how much meters are people? So if you take this case, you can suppose that, well, everyone has a height, so you want to measure how much people are tall in one country. Let's take Luxembourg, for example. So what you can do is you can measure everyone that live in Luxembourg, but it can be pretty costly, because even if Luxembourg is a quite small country, you have quite a lot of people, so it can take a lot of effort to measure everyone. And well, we can say that we can imagine that if you take only like half of the population or 25% of the population, it may be enough to have a good idea of how much people measure. And here you can see, so the interest of it is that we want to sample a population. We want to observe only a part of the population, and the goal is to infer on the whole population. So you measure the height on only 10% of the population, for example, and you want to know how much is the true mean of the height of people is closer to what you observed. Okay, so this is the idea of inferential statistics. So I will not go into detail of inferential statistics, I will leave you with some videos. So I really want you to see them because it's very important and it will be very useful if you work in academia later, or if you if you work in companies in the industry, it will be very useful. So the Simpson paradox. So you have three topics inside here, and in each three topics you have two videos. The first one is a short one, and it's mandatory. And then the second one of each topic is going to a bit more detail and is optional. But I really want you to see those videos to introduce you to some concept. It's important. Okay, so just to summarize you quickly, the Simpson paradox is basically kind of an introductory way to show you that if you use descriptive statistics and you are not careful enough on how your data is collected and how your data interact with other variables that you don't observe, you can go into false conclusion. So it's really important to keep in mind when we analyze data that we don't fall into some pitfalls. So this is a nice example of a paradox because it seems to be contradictory. Okay, hypothesis testing is maybe the most fundamental thing of inferential statistics. It's a very useful tool. It's also called statistical test, and it's basically a way to reject or not an hypothesis. So let's say that we have an hypothesis that can be generally it's statistics that is equal to one value. So you want, for example, to know if the height of Luxembourgish people is is equal to some value that you want to test, and you want to know if you can reject this hypothesis or if you cannot reject this hypothesis. So this is the idea of statistical test. An A/B test, I really put it in bold because this is the most important thing for you. And I really want you to watch at least the first video. The both would be ideal. I insist on that because it will be very useful for you to understand what is an A/B test, because it's a very nice and elegant way to evaluate what you have done and to evaluate how your users interact really with whatever services or whatever product you offer. So A/B test, the idea is that you have two versions, A and B. So if I will take the example of machine learning. So let's say that we have an old machine learning model that is deployed in production and that is performing some task. Let's say that we spend months on improving this model, having a brand new model that on our data works a lot better than what we have previously. So we are really happy because our new model perform really better. We have all the metrics say that it's better. The prediction are perform better, and it's good. So we have the impression that it's good on our data, but maybe we have old data in our training set, in our data set. Maybe it's too old. Maybe it's not really representative of what users will input in the system, because maybe we collected some image on the internet or some professional photography. Some images taken by really good cameras, and what the images of our user will input is some low quality images that are made by a cell phone. Maybe you can find a lot of ways in which your evaluation that you did on your data will be skewed, will be biased again than what you can expect from real data. So in that case, A/B test is a really nice tool because you can test whether your new model performs better than your old one in a real scenario, in the real environment. So the idea is that you deploy both models and then users will interact with the model randomly. So, randomly between the two. So basically, your user will be splitted randomly between model A, the old model, and model B, the new model. So this is really useful because then you can compare the metric that you are interested in and see if it's really performed better or not in the real context. So let's say that, for example, you have an image classifier, and your user can report if your classifier classify it badly or thing like that, and then you can see how much misclassification you achieve and are reported by your users. Then if it's equal or close enough, it can say that in the end you have the impression on your training data that your classifier performed better, but in reality it doesn't seem to be like so. Or and then you can use hypothesis testing to use statistics to give you an answer if you can reject the hypothesis that your new model is better than your previous one or not. So this is the idea of A/B test. The idea is really to use statistics to give you an answer. So another example is if you have a recommender system. So for example, in YouTube, you go to YouTube, you have always recommended videos, and you can see the click rate, how much percentage of the time people click on a new video. If you improve your recommender system, you can see, you can observe the click rate of your new model and the click rate of your old model and compare the two and use hypothesis testing to see if the two click rates are equal or if one is significantly higher than the other and things like that. So this is a really useful tool because it gives you an answer from real data and from the production data and from your real interaction with your users. So if you keep this tool in mind and if you know how to apply it, that's what I don't really want to give you all the internals about it because we don't have time. But I really want you to understand in what case it can be applied because it will be very useful for you in the industry because it gives you really an elegant way to answer a question. So yeah, I emphasize a bit the importance of A/B test because I think it's a really important tool and it allows you to make some decision based on data and based on quality data, quality analysis. Okay, so we see that in statistics, there is descriptive statistics and inferential statistics. Descriptive statistics is really easy. Inferential statistics is a bit more complicated because there is probability theory involved, but you can, if you are a practitioner, there is usually a lot of tools that will help you and that will help you to conduct such an analysis. So let's now review some concepts in machine learning and some vocabulary. So generally in machine learning, there are two phases, the training one and the operational one. In the training one, what you want to do is to estimate your model. So you give in input features and label if you have some. So if you are in the supervised learning case, you give features and label. And if you are in the unsupervised learning case, you give only features because you have no label. So you give that to your to the training algorithm of your model, and the training algorithm will output some estimation of your parameters. The parameters are the internals of the model. So what we call by learning the model, by learning from data, is really parameter estimation. So once you have some value for your parameter, you can go into the operational phase. And in the operational phase, what you do is that you have some features of new examples, of new data, and you input that along with the estimation of the parameter that you have, and you can output some prediction from your model. So these are really the two phases. One is learning, which is estimating the internals of the model, the internal elements of the model, and the other one is using what we have learned to do some prediction. So in the models is composed of parameters and hyperparameters. Parameters are really internal values of the model, and they are learned during training. The training phase consists of learning those parameters. And we call the learned value parameter estimate. So one example of such a parameter is a threshold and features in a decision tree. So here in the figure, we have an example of a decision tree. We start on the top, which is the root node in the root of the tree, and then you can see that at each node we have two child node, and each node have a condition associated to it. So generally, you have a variable, which is in the case of the first node, in the root node, it's temperature, and you have a threshold, which is 70 Fahrenheit degrees here, and you can evaluate if it's true, if the condition is true, or if the condition is false, and you can explore the tree like that, browse the tree. So at the beginning of the learning phase, you have basically a blank shell, a blank template of your decision tree, and you want to fill it with the condition, and at each node you want the feature associated to the condition and the threshold. So once you have learned this, you will produce this type of decision tree. So really the parameters here in the decision tree is the features and the threshold at each node of the decision tree. Okay, so once you have learned this model, this parameter, you can use it as we saw, in the operational phase, it's the prediction phase, and you have a new example. And you will, with this new example, you will evaluate at each node the values. If each condition is true or false. If it's true in the root node, you will go to the left, and then you will evaluate on the left child if the wind is more than 2 miles per hour. If it's more or less, you explore the right-hand side or the left-hand side of the tree, of the subtree, and then you continue until you reach a leaf node. And you can see in the leaf node that here we have either rain or not rain, and this is the predicted label. So you can use the decision tree like this. So it's a very simple model. And the nice thing is that you can interpret it, you can look at it, plot it like this, and see how the decision is made. So let's get back to the parameters and hyperparameters. So some internal values, some elements of the model can be learned, but some cannot. And this is what we call hyperparameters. So hyperparameters are the same as parameters in the sense that they are internal values that influence the model, but they cannot be learned, as we said. So, and an example of such a hyperparameter for a decision tree is the depth of the tree. So it's the maximum number of nodes that you can evaluate to go to a leaf node, to go until the end of the tree once you have new data coming. So here the depth of the tree is you have the root nodes, you have the first layer, the third layer, and the leaf node. So here it would be 4 or 3, depending if you count the root node and the leaf node as a node. But you get the idea. So here, what I want to show you is that you can have some internal value of the model that can be learned, parameters, and some that cannot be learned, hyperparameters. And if we have some hyperparameters, it's because the way we define models, we need sometimes some internal value to define them that can be tuned, because if we cannot have fixed value. For example, we cannot say that for every data from every decision tree, the depth of the decision tree will be 8, for example, or it can be, because sometimes 8 will be good, sometimes you want a decision tree which has a maximum depth of 4, sometimes you will want 20 and things like that. So you get the idea. If we fix by default the value, this type of values for all the data that we want to model, well, it will be too restrictive. You want to have some hyperparameter to allow your model to be different and to allow some flexibility depending on the type of data that you will train your model on. So because here, for example, we can expect some different type of complexity. If we have a small depth of a tree, it corresponds to some simple data, like for example, the spam filtering case, which is pretty simple task. But if we, for example, take the classification of images of cats and dogs, it's a much more complicated task. So maybe we will need a much deeper tree. Okay, so now we will see some consideration of statistical learning theory. So we will only see 2 or 3 ideas inside the statistical learning theory, which is the theoretical study of machine learning. So it will be the most theoretical part, but I hope that you will be able to grab some insight from it. And it's theoretical, but it will, as you will see, when you will practice it, is very useful, especially to understand some complex and some pitfalls that you will definitely encounter when you will train some machine learning model in the industry or in the academia. And yeah, because it's we can grab some very fundamental properties of machine learning. So we have seen that in the training phase we are learning from data, but how can we learn from data? Because it's not a very natural way to. We don't know. A priori how we learn from data. So here we will not fxi the prediction of the model that is outputted by the model for the example number I. So in order to learn from data, we need the model to know when it performs good and when it performs badly. So for that, we define the loss function. And the loss function is really a function that will give a measure on how far the model prediction is from its label. So here we have an example. We have We pass it through the model, we have the prediction, and we have the true label, and we compare the prediction and the true label. If it's far away, we have a higher loss than if it's closer. So in the binary classification case, which is the case, for example, for spam filtering, we just take the loss. So here it's a mathematical notation, but the idea here is that if the prediction f of xi is equal to the label yi, in this case, if it's equal, the loss will be equal to 0 because there is no error, basically. If it's different, so if, for example, we say that it's a spam, the model, said that it was a spam, predicted a spam, and it was a ham, it was not a spam, then we will set the loss equal to 1. So you can see that the loss, for example, in the binary classification case, said that it's a way to measure if the model performed good or performed bad. So using that, we construct what is called the empirical risk. So the empirical risk is just the average of the loss computed on all the examples of the dataset. So here we compute the average, and it's an indication on what is the accuracy of our spam filter, for example, in this case. And what we want to do in the end is to minimize this empirical risk, because we want to minimize the empirical risk. Sorry, I just realized that I said that empirical risk was like accuracy, but it's 1 minus accuracy, because if the accuracy is equal to 1, it means that we do something perfect. We never make mistake, and it will mean that the empirical risk will be equal to 0, because the risk is like the error. And if the accuracy is 0, like we are always wrong, then the empirical risk will be equal to 1 in the binary classification case. Okay, sorry for this mistake. So here the idea is really that when we want to learn the model, when we want to train on our data, what we want to do is to find a function f, which is, as we recall from the first video, the mapping between x and y, between the features and the label. And we want this to be as minimal as possible, because it will give you an idea that that we want to minimize the error. So just a quick note, here for simplicity, we are only on the supervised learning case, for those who are wondering. So you may wonder why it's called empirical risk. So we called it empirical because the idea is that in absolute, in theory, what we want to do is to minimize the risk across all the occurring examples, all the possible examples that we can see. So, for example, if we are talking about spam filtering, we don't want just our model, our spam filter, to work on the previous email that we received, but we also want it to work on all the emails possible, all the spam that can exist, and all the non-spam that can exist. Obviously, it's not a finite case. We don't know all the mails that is possible to write. So really the idea here is that the true risk, which is the risk computed in average, which is a theoretical thing, it's the risk of all the possible emails that we can encounter, that can be generated by people or by machine. And we want this risk to be as minimal as possible. But it's a very theoretical risk. We cannot compute it. So instead, we will try to minimize the empirical risk. So the risk computed on the data that we have, on the data set. So here, for example, all the emails that we received. So another example is the image of cats and dogs. So when we build a classifier to classify images, if it was a cat or a dog, what we want to do in the idea is to have a classifier that can classify all the possible images of cats and dogs, not just the ones that we have in our dataset. So obviously it's the same than for email. It's not a finite. It's not a finite number of images that is possible. You have an infinite type of an infinite set of images that you can imagine. There is an infinite set of images of cats and dogs in the absolute, in theory. But so we'll replace here the theoretical risk by the empirical one. So just the main idea of this slide is really that in order to learn, we define a function, the loss function, that characterize what the model does good and what the model does bad. And it's kind of a way from the model to learn from his mistake. So, yeah. So one important thing in machine learning is called overfitting and underfitting. But before going into that much detail, let's study the decomposition of the error. So in the equation here, you have a different type of F, so different type of classifiers. Let's just review them for the moment. So Fn is the train model that you have. So you train your model on the data and you have one model. This is really the model that you can access, the model that you have. The F bias is a theoretical model. You can see it kind of the best model that is possible with the current set of features that you have. So with the data that you have, with the information that you have. So you can see it as the best model. So the risk of this best model, you can see it as the minimum possible that can be achieved with the features that you have. So you can say that you may think that the best risk that you can have is 0. So this is true in some case. In some case, the best model possible can be 0 if you can perfectly classify it. But you can imagine that if you are in the features, in some complicated case, if you are missing some crucial information, some crucial features that you don't observe, well, maybe you don't have enough information to separate the label from another label. So if you don't have enough information in this case, the best thing that you can do may not be the risk of the best classifier that you can achieve may not be 0. So okay, I just want you to recall that the risk of the kind of best classifier may not be 0, but it's basically a reference point. You can see it as the minimum risk that you can have. Okay, so Fn is your training model. F bias is kind of the best model that you can have. And you have another function, which is F and F and capital F. So this one is also a theoretical model. It's a theoretical function, and it corresponds to the best one that you can do with the chosen algorithm, with the algorithm that you choose, and also the current set of features. So let's imagine that we choose some decision tree. We choose to train a decision tree. So the decision tree that we trained is Fn. The best classifier, the best model that is possible on our data is F-bias. So it can be maybe the best thing that we can do correspond to a decision tree, but probably not, because you can imagine that building a decision tree, building some binary split and splitting our example with some threshold is kind of restrictive. So if you can imagine all the possible models that you can do, it's probably decision tree is probably too restrictive on real data. And FF here correspond to the best decision tree that you can achieve. Okay, so let's review what we see. The left side of the equation correspond to the difference between the risk of your model and the minimal risk, and this can be decomposed between the right part of the equation, which is composed of the estimation error and the approximation error. So the estimation error that you can see on the left. Just before, you can see that there is a math, but it's really easy. We just subtract on the left-hand side the risk of FF, and we add it on the right-hand side, the same element, the same risk. So we just added a value and subtract it. So it's nothing complicated, but we have to analyze it because it's allow us to think and to make some important consideration. So let's review what's the estimation error. So the estimation error is F, the difference of the risk of your trained model and the risk of the best model that you can achieve with the chosen type of model that you choose. So in the decision tree case, you can imagine that you train your model on some data. You train your decision tree, on your data, and the estimation error may not be zero because generally it can be complex and really too intensive to search all the decision tree, because if you have some continuous feature, for example, when you have to set a threshold, you need some greedy approach in order to solve the finding of the tree, to train your model to find the conditions and such a thing. You need some greedy approach to be able to compute it in some reasonable amount of time. So you will probably not find the best possible decision tree once you're trained, unfortunately, because you have to make some consideration to improve the speed of the training phase. Okay, so the estimation error really corresponds to the gap that you do once you train your model between your best model possible with the chosen algorithm that you choose and the one that you have. And you can see on the right part that we have also the approximation error. So the approximation error is a theoretical thing, because you can see that the two parts are the risk is we compute the difference between the risk of FF and of the risk of F biased. So here, the idea of the approximation error is that it's a characterization of the algorithm that we choose. Basically, if the decision tree, for example, is too restrictive, is too simple, it may not be able to grab the complexity of our data. So we may choose some decision tree because it's easy to train, because it's quick, because it's interpretable. And so you have some advantage like this. But you have also some drawback because maybe the decision tree is too simple. So for example, in the case of classifying images of cats and dogs, you can imagine that if you have only the values of the pixel and you build a decision tree just by splitting if such a pixel has a higher intensity value than a specific threshold, and you explore different pixel value like this, it will be very difficult to learn the patterns of what a dog and what a cat look like. So maybe probably the approximation error will be quite big here because basically the chosen algorithm, here the decision tree, may be too simple. Okay, so just as you saw on the figure in the right part of the slide, we have two circles. The inner circles correspond to, as you see, to the function space that is used by the algorithm. It's basically all the possible decision trees if we take the example of the decision tree. So we choose a decision tree as the algorithm, and this inner circle is all the decision tree possible. And the outer circles is all the model possible, all the prediction function possible. So you can imagine any model, any function of prediction possible. So it's a huge space. All the possible decision tree is already a big set of functions, but you can understand that the outer circle is even bigger. Okay, so here you can see that Fn is inside our inner circle because it is a decision tree. It is a model that is corresponding to the algorithm that we choose, and Ff, which is the best decision tree possible, is also inside the inner circle. And as we said, the best model, F-bias, is probably outside of our inner circle because, as we said, we need the inner circle to be not too big in order for us to train our model. So that's why you can see that the difference between of risk, the difference in terms of risk between Fm and Ff is the estimation error, and then the difference between Ff and F-bias is the approximation error. So the estimation error is also called sometimes a variance, corresponding to a variance, and the approximation error to the bias. And a very famous thing in machine learning is called the bias variance trade-off. So what does it mean? It means that generally we are not able to find models and to train models that have low bias and low variance. Generally, we have to find when we train and when we choose algorithm to find some trade-off between the two because it's very hard to have both low. So yeah, this is the bias variance trade-off. The bias correspond to the bias, as we said, correspond to a large approximation error and a small estimation error, and we call that underfit. Why? Because the idea here is that when you underfit, it means that your chosen algorithm is too simple. So it's not able to grab all the complexity of your data, and that's why we have a large approximation error because we approximate too much the data. When we approximate the data, we make large errors. But in the same time, we make small estimation error because remember the two circles. and if our inner circle is small, it will be easier to find the best function, the best predictor, the best model inside this inner circle. It's like you restrict the space is small, it's easier to find the best function inside it. In the other case, when we have large variance, it corresponds to large estimation error. So in that case, we choose an algorithm that have a bigger inner circle. So our inner circle is much bigger. It's much closer to the outer circles. And in that case, you have the space where you have to search for the best model possible is much larger. So you can think a bit, it's like finding a needle in a haystack. So it's very hard because you have to find the best model inside a very huge space. But if you inside the space, this space is probably, if it's big, then it means that you probably have a small approximation error, because it means that as your inner circle grows and grows, you are closer to the best possible classifier, to the best possible model. Okay, so here the idea is basically that we have to find a trade-off between the two. So we have to find a space of functions, an algorithm that allow the space of possible model to be big enough to have enough complexity to model the data, so to not be too restrictive and too simple. But we don't want it to be too big, because if not, it will overfit. And that's what when we have high variance, it corresponds to overfitting. And overfitting means basically that we learn kind of too much. We learn all the data. So if we take an example, it can be, if we take if you can allow me the comparison, it's like a student that is learning exactly words per word what the professor is saying. If the student is like learning by heart all the sentences and all the specific sentences that are pronounced in the course, it will not grab what is the true concept of the course. The student will not understand the content of the course. So it's kind of like this. If a model is learning by heart each specific example, it will probably not understand the true signal of the data and understand what is, for example, the specificity of a cat and what is the specificity of a dog. If it learned by heart each pixel of each image is inside the dataset. So let's take this example. So here, in the figures that you can see in the slide, in the horizontal axis, we have a feature. And in the vertical one, we have the label. So here, it's a regression, because you can see that the label is a continuous variable. So in the center, we have kind of an ideal function. It seems to be pretty good, because in average, the distance, the vertical distance between the dot and the curve is quite small. So we say that it's a good fit because it's learning kind of the true signal. But you see that it's not perfect, like you have still some error. So if you take a vertical bar between one dot and the corresponding point in the curve vertically, it corresponds to the error of your model. So let's take the left part, the left subfigure. So here we draw a line, the red line. So you can see that drawing a red line is pretty good. Like we kind of understand that the features is negatively correlated to to the label, but we kind of make we make pretty big errors in average because the curve is quite is pretty distant vertically from each corresponding point. So it's we call this underfitting because it's kind of an oversimplification of the data. Here the model suppose that we can draw an horizontal we can draw a line in the data, and the points are not so linear, so it's an oversimplification of the data. We can learn more from the data. But on the other case, in the right-hand side of the figure, we can see that it's overfitting. Here, we are trying to learn so much from the data that we are overfitting. We are learning the noises of the data. So we are learning the true signal, but also the noise, and it can hurt because it can hurt our performance because you can see that on the blue dot the error is very small. So we can think that, oh well, it's good because I'm like the error on the blue dot is very small. But for example, let's take a look at what happened close to the when the feature is equal to 2. You can see that it's dropping very quickly to very negative value, to very small values. And we can think that it may be really strange for it for such a small variation in the x in the feature to drop so much, to have a prediction that is so different when we change a bit. So probably here we allow the model to be so complex, to be so to be so free, to have so much freedom in the end that the model wants to fit to the blue dots, and maybe he fits too much and he wants to be too close to that, and he misses the true signal. So let's I talked about noise here because in real data you always have some noises in the data. The noise this type of randomness can come from different sources. It can be either that when you observe the feature, when you observe the data, you can have some noises. So for example, if you take some physical measurement of the age of people, then well, you have a precision, specific precision that is associated with each measurement in meter. It can also come from natural occurring randomness. So if you take 2 times the same value, it may not be exactly the same number, and it can also be that you don't observe some key information. You don't have all the features. You may have some unobserved features that is adding some noise when you plot only some features, when you are using only the features that you have in hand. Okay, so here the important thing is that underfitting is an oversimplification of the data, and underfitting is an oversimplification of the data, and overfitting is fitting the noise of the data. So for those who are curious here, we are training some polynomial equation so to fit the data. Okay. So in this case, we have still in the overfitting and underfitting case. So we can plot in the horizontal axis the model complexity, and we plot for each type of complexity the average error in the left-hand side, in the vertical axis. So you can see here that we have 2 types of error: the blue one, the training error, and the holdout error, the red one. So to take a step back, what we do generally in machine learning is called cross validation, And in cross-validation, what you do is that you take some example, the training example, the training set that is used to compute the blue curve, the training error, and you feed this example into the training phase so your model is learning from the training data. And what you do is that you keep a separate dataset without intersection between the two. So each example, you have no example that is both in the old out dataset and in the training one. So why we do that? We do that because you may remember what we said is that if the model is very complex, the model will remember by heart the specific example. Like if you have a very, very complex model, it will remember each pixel of each images of cats and dogs that you give to him. But we don't want that. And to have an idea of what is the true error, what is the true error of new images that will give to the model, we keep some images, some example away during the training phase, and we predict them and we compare the predicted label with the true label. And it's a nice idea because the idea here is that it's an unbiased estimate of the error, the true error, the one that we are interested in, because the model was not trained on those examples, so it was not able to overfit it, to learn it. Okay, so here let's take a look again at the figure. You can see on the lower part that we have that both holdout error and training error are moving in the same way when we increase model complexity, and they are pretty close to each other. So this is because remember that in the underfitting case, in the high biased, we have an oversimplification of the data. So in the previous slide, we just drew a line where the relation between the dots, between the feature and the label is not linear. So we have high error between holdout and training, and they are evolving the same way in the sense that the model is not complex enough to grasp all the complexity of the data. And then when we move to the right, when we have a lot of complexity, the model is allowed to model a lot of complexity, then we start to remembering all the training example. And then we see a very different error between the one that is computed on the training set, so the one that is that the models was trained on, and the holdout error. This is really an example of and an indication that we are in the case of overfitting. It means that if your training error is very low and your holdout error is very big, it means that your model have learned so much from the training data learned by heart that it doesn't generalize well with new data, the data that it doesn't see. And here you can see the bias variance trade-off. And what we want is that we want a kind of a model that is complex enough, but not too complex. So we want kind of being in the middle. Okay. So I hope that you understood what is biased variance trade-off and what is underfitting and overfitting. Okay, so you will see if you work in the industry or if you work in academia that overfitting and underfitting is really a key concept and something that we always have to wonder. And it's very, very important. Okay, so this is all for this first session. You will see on Moodle that I put some quizzes so you can answer them. We will go into the quizzes. I will ask you some questions about what we saw, and the idea here is that you feel it, and it will allow you to think about what we saw and to think about some maybe edge cases or some cases. And I really encourage you, and I really want you to feel it because you will able to understand it better. Okay, and I will also normally the on Moodle we will also open the forum part. So if you have any question, you can ask on the forum, and I will go on periodically to answer them. Also, if you have some answer, you can answer to your friends there. Okay, so let's see you on Moodle, and I see you next week for the next session.